I just finished a lesson on registers for my class, and I wanted to read this guy's blog for the students who just enjoy kicking back and listening to me explain things to them. So I'm going to do a lot of straight reading from this, and then I'll go ahead and make my comments throughout. By the way, Ken Sheriff here is a genius of a man. He gives some pretty interesting talks. You can find them on YouTube. And he is all about the low level, my favorite place to be. So the title of this post is Reverse Engineering the Surprisingly Advanced ALU of the 8008 Microprocessor. What's the difference between a microprocessor and microcontroller, you may wonder? Well, a microprocessor relies on accessing memory outside of itself, and we're talking RAM level memory. Technically speaking, a microprocessor is an integrated circuit, and on this integrated circuit, there is a central processing unit. That's it. So here we are looking at a device that is just a chip. So it says, a computer's arithmetic logic unit is the heart of the processor, performing arithmetic and logic operations on data. If you've studied digital logic, you've probably learned how to combine simple binary adder circuits to build an ALU. However, the 8008's ALU uses clever logic circuits that can perform multiple operations efficiently. And unlike most 1970s microprocessors, the 8008 uses a complex carry look-ahead circuit to increase its performance. So if you're taking notes at home, carry look-ahead circuit in up arrow performance. I've never heard of a carry look-ahead circuit. And we're talking some old tech here, 1970s. So it says the 8008 was Intel's first 8-bit microprocessor, introduced 45 years ago. While primitive by today's standard, the 8008 is historically important because it essentially started the microprocessor revolution and is the ancestor of the x86 processor family that you're probably using right now. I recently took some dive photos of the 8008, which I described earlier in this article, and I reverse engineered the 8008's ALU circuits from these dive photos and explain how the ALU functions. And I'm pretty sure this guy has a website of dive photos. That's what a dive photo is right here, so my note takers. It's die as in the skull and crossbones kind of die. And this is pretty impressive. He says he reverse engineered this from the photos. So the image below shows the 8008's tiny silicon die, highly magnified. Around the outside of the die, you can see the 18 wires connecting the die to the chip's external pins. The rest of the chip contains the chip's circuitry, built from around 3,500 tiny transistors, which is in yellow apparently, connected by a metal wiring layer, which is in white. Now, many parts of the chip work together to perform an arithmetic operation. First, two values are copied from the registers, which is on the right-hand side of the chip, to the ALU's temporary registers, which is on the left side of the chip, and it's doing this via the 8-bit data bus. So the ALU computes a result, which is stored back into the accumulator register via the data bus. And he wants us to note here that the data bus splits and goes around both sides of the ALU to simplify the routing. And here is the moment we've all been waiting for. The carry look-ahead circuit generates the carry bits for the sum and parallel for high performance. So one more time, the carry look-ahead circuit generates the carry bits for the sum, and it does this in parallel. This is all controlled by the instruction decode logic in the center of the chip that examines each machine instruction and generates signals that control the ALU. So it sounds like this decode part of the chip is doing us a great favor by giving us a heads up. The heads up to allow us to control the ALU. So let's learn more about the ALU here. It says the 8008's ALU implements 4 functions. Yay, who said computer science is hard? The 4 functions are sum, and, XOR, and OR. For my students, my first-year students, I highly suggest they download this game called Circuit Scramble just to really wrap your mind around the concept of chain reactions being caused by a chain of different binary bits. Or I should say the ones and zeros that you can see at the bottom of these pictures here. So you need the right permutation, the right order of ons and offs in order for the electricity to flow in just the right way to light up the screen at the end. And if I designed this game, I would have turned these little spinning wheels into actual chips that say inverter on them. But nonetheless, over here, this guy is just saying there are 4 functions to the ALU, and here they are. Not very complicated. The sum operation adds 2 8-bit numbers. Big surprise. The remaining 3 operations are standard Boolean logic operations. The AND operation sets an output. Okay, I'm going to skip this part because if you're watching, you should already know that. Now, the concept of carries during addition is a key part of the ALU, right? You can't make a sum from 2 large numbers if you don't have a carry bit. So if you're doing anything more complicated than 0 plus 1, you are screwed without the carry. So the concept of carries is key. Binary addition in a processor is similar to grade school long addition, except with binary, numbers instead of decimal. Starting at the right, okay, I'm going to skip that part too. In most early microprocessors, addition of each column needs to wait until the column to the right has been added and the carry is available. That makes a lot of sense. The carry ripples through the bits, right to left, slowing the addition. The 8008, however, uses a fast carry look-ahead circuit to generate the carries for all 8 columns in parallel before the addition happens. Wow. I really wish right here in the blog he had the picture of the adder that I make my first-year students create. This adder, full adder, is how the magic of using electricity as an input can ultimately result in some sort of output that is the correct answer to an addition problem. Maybe I can reach out to this guy and offer that picture for him to place right here. But nonetheless, then all the columns can be added in parallel without waiting for the carry to ripple through the sum, and this carry look-ahead circuit is an unusual feature to see in an early microprocessor due to its complexity. Since the 8008 is an 8-bit processor, the ALU operates on 2 8-bit arguments. Most 8-bit processors, including this one, uses bit slice construction for the ALU, with a 1-bit ALU slice repeated 8 times. Each 1-bit ALU slice takes 2 input bits and the carry in bit. This is what produces the output bit. So in most 8-bit processors, the bit slice, such a cool term right there. The bit slice ALU is arranged by stacking 8 rectangular ALU slices to form a compact regular block. However, the 8008 has its 8 ALU slices arranged in an irregular fashion. Some blocks are even sideways right there. The motivation for this is that the carry look-ahead circuit takes up a triangular space on the chip. To fit the remaining space better, the 8008's ALU is arranged into its unusual triangular layout. Right here, if you could see the triangle, maybe he could have done us visually challenged or reading challenged students a favor and drawn the triangle right here. But this is why I read these blogs to you guys, so I can assist you. It says, zooming in on the die photo, we can look at one of the ALU slices and see how the circuitry is constructed. The chip is built from 3 layers. To simplify slightly, the topmost layer is the metal wiring. It is the most visible feature and looks metallic, not surprising. In the detail below, you can see the horizontal and vertical traces. So when you're looking at like a motherboard, circuit board, these little lines are called traces. Oh, there's a bigger photo of that for you. The polysilicon layer is underneath the metal layer and appears yellow-orange under the microscope. Polysilicon can act as wiring, but more importantly, it forms the gates of the transistors, switching them on and off. Now, the bottom layer is the grayish silicon die itself, but it is hard to see under the other layers. So wow, I can't believe a microscope can show us this stuff. I don't feel so silly for having students draw these things in class now. In the diagram above, the carry, C, and the complemented A and B inputs enter through the metal wires at the top, and the ALU output is at the bottom. The control signals are horizontal metal lines, and the circuit is powered by the 5 volts and -9 volt metal lines. The brighter yellow polysilicon regions are transistors, and each gate in the circuit requires a load resistor connected to that -9 volts to pull its output low. For improved performance, these are implemented with transistors rather than resistors. Okay, so we're getting really electrical engineering here right now. For the sake of this class, I don't want to go that deep. So let me just scroll down to some cool pictures and we'll wrap up this video. While the ALU slice looks like it is made of mini gates, physically it is only 3 gates, 2 large multi-level AND/OR NANDs, and 1 NAND gate. The AND or NAND logic is implemented on the chip as a single complex gate rather than combining simpler gates, and since a single large gate provides better performance with less circuitry than multiple small gates, one feature of the MOS logic is that it's just as easy to form an AND or NAND gate. For instance, it's saying it's easy to form one of these, for instance, and that's compared to creating just a plain NAND gate. So it's rough if you're in class and you're looking at one of these, you don't know what this symbol means. It might be worth your time to try to memorize these here. So this is an AND, this is the AND, an OR, and then where's my favorite? There we go. This must be an XOR. It says EOR though. XOR is the favorite one of mine. Why does it say logic gates for PowerPoints? Maybe I didn't choose the best pictures. I like this one. Oh, this should go in your notebook, you note takers. It has everything. Maybe skip the truth tables, but make sure you understand what these are in relation to the truth table. So let's go ahead and end this video here. How about I make a follow-up of this, and I'll call it Understanding the ALU Logic.